Let's get into it. We'll just do maybe quick intros first, but I guess for starters, this is going to be our talk, discussion, presentation on multi-round interactive proofs, how and why. For those who don't know me, I'm Daniel Goldman. I'm an engineer here at Off-Chain Labs and also do, technical communication, let's just say broadly. Ed, you want to give a quick?
Sure. Hey, everybody, I'm Ed Felten. I'm a co-founder and chief scientist at Off-Chain Labs. And I do a whole bunch of engineering, some protocol design stuff. Harry.
Yeah, I'm Harry. I'm also a co-founder of Off-Chain Labs and CTO, and do a whole lot of engineering.
Cool. So I guess to get started, for a bit of context, we did a Q&A session last week, and we got a series of questions from Eric Wall that were very focused on sort of the benefits of multi-round proofs for optimistic rollups versus sort of single round. And we'll get into some of the specifics of those questions in a second. But basically what, from sort of thinking about it, we want to get into this question, but it's sort of impossible to answer that without getting much deeper into the sort of core Arbitrum protocol design. And it's the more I thought about it, I thought this takes, an entire session just to do. So here we are. I think the sort of key takeaway here that we're going to see is that, when you talk about this distinction between our system, Arbitrum, and something like Optimism, the sort of surface level comparison is what I said. So fraud proofs are handled via this interactive process versus via a single round. Oh, Harry's dad is here. That's cool. Sorry. So that's kind of, in a way, that is a bit of a red herring. I mean, it's true that is a difference, but it actually sort of is just the starting point or the entry point to a much deeper difference in how these protocols handle emulating a virtual machine on layer 2. And essentially what we'll sort of see is that the Arbitrum way of doing things involves full virtualization of a virtual machine, whereas the Optimism way of doing things involves the ability to sort of containerize and emulate a virtual machine on layer 1. And if it's not clear what I mean by that, hopefully by the end it'll at least be clearer. What I see what you're doing there in chat. I lost my train of thought. What was I saying? Yeah, so the idea is like, what you'll see is, as we sort of unpack that distinction, is that these design decisions are actually very different. And in terms of where complexity emerges in both of the protocols and the sort of implications there's a lot of like surprising, weird, and I think kind of interesting design differences that we will get into. Anything else to add there, Harry, before we dive in?
I mean, I think that pretty well covered it. I mean, I think this should be an interesting session because I feel like we've been building this stuff for years now. The Optimism team has been working on their stuff for not quite as long, but for quite a while now. But we've been and obviously we're pretty familiar with what they're doing. They're pretty familiar with what we're doing, but we haven't kind of had much in the way of sort of direct, and people haven't done much in the way of kind of direct comparison. And we've kind of haven't done we haven't wanted to do too much of it ourselves, just because everybody's focused on building it, but I think the question comes up a lot, so I think it should be pretty interesting to talk about it a little bit.
Yeah, for sure. And one other thing I wanted to add, if anyone listening has questions, feel free to ask questions in the chat. For this, sometimes we do more open-ended Q&As, but for this one, we do want to focus on sort of this topic at hand. So questions around, basically around this are the ones we'll take. If you have something else, we'll probably get to it at some other point. But okay, let's sort of get started. So I guess first things first. So if you're at all familiar with optimistic rollup, which you probably are if you're here, the thing that you probably know is that the basic idea is that instead of sort of doing all this work, is that we have some transactions that are taking place on layer 2. which means that instead of doing the work that we usually do on layer 1 of directly verifying them and ensuring that they're valid, we sort of optimistically assume they're valid, and then if there's any disagreement, we can sort of adjudicate that back on layer 1 and sort of prove fraud. So what we want to start getting into is the question of, well, how exactly? How do we prove fraud? So as we said, in the case of Arbitrum, this is sort of a multi-round interactive game. And yeah, let's start by just sort of describing that, this question of like literally what, how does the Arbitrum protocol actually handle proving fraud? So yeah, I'll open it up. I'll open it up to Ed to get us started there.
Hey everybody. Yeah, so let me first set up this scenario. So here's the scenario. A lot of people have submitted transactions to an Arbitrum chain, and those have been put in batches into the chain's inbox. And now Alice is going to make a roll-up block, we sometimes call an assertion, which is claiming what the result of the next group of transactions will be. And so let's assume that Alice's roll-up block that she claims covers 1,000 transactions and 10 billion steps of computation altogether. Okay, so that's 10 to the 10 steps of computation. So Alice posts her claimed roll-up block, and it says, okay, the virtual machine is going to execute 10 to the 10 instructions, and at the result of it, here's what the state root will be, a sort of hash that covers all of the state of the virtual machine. And then she also makes a claim about what outputs it produces, like which withdrawals happen from the chain and stuff like that. Okay, so Alice has made this claim, and then of course there's a window of time where someone else can show up and disagree with it. So in our story, we'll say that Bob decides to dispute Alice's claim. So Bob says, no, I disagree with Alice's claim. I say the result of executing 10 billion steps of computation, starting in the same state as Alice, is something else. So Bob makes his specific claim about what he thinks the result should be. And now we get to what really the crucial step, which is bisection. So Bob, in addition to saying, here's what the result is after 10 to the 10 steps, the full claim that Alice has made. Now he has to break that up into 100 pieces that are 1/100th as large. So he posts the difference after 10 to the 8, 2 times 10 to the 8, 3 times 10 to the 8. He posts what the state root is at each of those points. Okay, so what he's doing is he's taking his 10 to the 10 step assertion, he's breaking it into 100 assertions, which are each 1/100th as large. Now Alice, now the ball is back in Alice's court. Bob has made a claim that's different from Alice's, and he has dissected it into 100 pieces. Now what Alice has to do next is she has to point to one of those 100 pieces that she says is wrong. If she disagrees with Bob, there must be something Bob's claiming that she disagrees with. And so she picks one of those intervals, the size 10 to the 8, and I guess 100 million, and she says, I disagree with that one. And now Alice has to say, in her response, what she thinks is the correct result. Instead, at the end of that little 10 to the 8 size chunk. And then she has to break that into 100 sub pieces, each of them 10 to the 6 or 1,000,000 steps in length. Right? Once Alice has done that, now the ball's back in Bob's court. He's got to pick one of Alice's 100 smaller claims and dispute that. And then he, in turn, makes a counterclaim, divides that 100 ways, and so on. So each time a player moves in the game, they first of all say what they think is the right answer, which has to be different from what the other person said. And then they break their claim into 100 pieces. So you go down to a disagreement. So what you're doing is in every round of this game, you're reducing the size of the execution that they disagree about by a factor of 100. So after 5 rounds of this, you're down to a disagreement about one step of execution, like say just an add instruction. So if Alice and Bob have narrowed their disagreement down to a single instruction, now let's say that Alice is making a claim about what the result of that one step of execution is. Now Alice needs to actually prove what the result of that one step is. We call that a one-step proof. And that and that actually gets checked. Okay, so it's a back and forth process between Alice and Bob. It's like a 2-player game, and there's a referee in the game. The referee is an L1 Ethereum contract, which is part of Arbitrum. And that referee makes sure that each player, when it's their turn to disagree with the other player and then subdivide, actually does disagree and does provide 100 claims about what the smaller intermediate steps are. And then at the very end, when there's a disagreement about one step of execution, then the referee just checks whether that one step is correct. So if the step is an add instruction, then Alice, that adds the top 2 items on the stack, on the machine stack, then Alice needs to say, okay, here's what the top 2 items on the stack are at this point, and here's my proof of that. It's an add instruction, and here's my proof of that. And then the result of adding those things is whatever it is, right? So it's bisection or dissection by about a factor of 100 at each round, and then a 1-step proof, back and forth between Alice and Bob. So this is a very efficient way of resolving the dispute, because the referee's job is super simple. Did Alice move or Bob move on time? Did they make a claim about when they contradicted the other person's claim, did they make a claim that was different? And did they, in fact, produce 99 intermediate points like they were supposed to? And then only at the very end does the referee actually need to look at anything about what the machine does on the merits. So anyway, that's how Arbitrum does it, bisection followed by a 1-step proof.
Yeah, so just to reiterate a bit, I think the key intuition here, at least for me, is that, if Alice and Bob disagree about the result of the state update, it must be that there's a single instruction, at least one instruction that they also disagree on. And basically this whole interactive process is mostly, the whole thing is about just zeroing in on what that little tiny disagreement is. And that process of zeroing in doesn't actually, you're not actually doing any of this L2 execution until you actually find the 1 step, and then you just execute that 1 step. And in that way, the sort of L2 virtual machine is something that the base layer doesn't have to do that much work on. It just has to do this actual bisection, or I guess dissection, and then it just needs the ability to execute a single AVM instruction.
So 2 things about that. One is, first, this idea that Alice and Bob are doing the work to figure out what is the first instruction of execution where they disagree. That's obviously an important thing. And the other thing is that the technical property that makes this thing work, which is pretty easy to prove to yourself, is that the party who is right can always win the game, can always win this process. A party who makes a correct assertion can force the other party to always make false claims. And so if you're right, you can always win this dispute. And this is what leads to the global property of Arbitrum, that one party who's telling the truth can force the correct execution, even if everyone else in the world is against them. Because that one party, by virtue of being right, can actually win any dispute they get into.
Yeah, because if you're right, actually every individual step is right. So wherever you end up in this bisection or dissection, you end up being able to pass the 1-step proof. So just need one honest party.
Yeah.
Good.
So if you're right, then the other party, they're forced. The rules of the game say they have to disagree with you, and so when they disagree with you, they'll be wrong, which means you can always rebut them with something that's correct, right? And so if you're right, you can always win the game, and it's pretty easy. All you have to do is tell the truth.
Yeah. So in terms of the benefits of doing it this way, and this is sort of there's no easy way to summarize this. It's probably a lot of what we'll be talking about. But the first thing is, again, it's good to just sort of understand that this process, in terms of what layer 1 actually needs to do, is actually in a way surprisingly simple. So one of the questions that we got asked is this issue of state root commitment. So where on something like Arbitrum, we don't need to sort of commit to as many state roots in the optimistic happy case as they do on optimism. And this is fairly straightforward, where essentially, I think the way Harry likes to put it is, we sort of, with a single round proof version, the sort of state transitions are pre-bisected. So even in the happy case, you post all of these state roots, whereas in our case, we sort of bisect in real time and post state roots as need be. So instead of having every state transition be a single transaction and having state roots for each transaction on chain, we can just sort of say a whole bunch of transactions. We consider one big state update, and then we only do this extra work if challenge arises. So that's like one benefit, where essentially like, okay, we don't need as much data on chain. We don't need to like serialize state as often. We can save some gas, yay. But again, that's sort of like the most surface level benefit to this. Where it gets, I think, more interesting is when we sort of compare the sort of, the pessimistic case, the unhappy case where we have to do this fraud proof, which I've described, to sort of the alternative if you're committed to resolving a dispute in a single transaction, a single round fraud proof like Optimism does. So what happens there, if we sort of shift gears to the single round version of things, which we don't do on Arbitrum. So again, what this kind of looks like is, okay, you have a transaction which says, okay, here's the old state. I'm declaring that this is the new state at the end of the transaction. And let's say that state transition is invalid. So again, Alice and Bob kind of disagree. So Alice was dishonest. Bob now has to prove that Alice was dishonest in a single transaction. Okay, so the basic idea is what you do is you just execute that transaction on L1, right? But what does that entail? So in the sort of single round optimism model, that entails a few things. So first of all, in order to actually do this execution, the transaction is going to sort of depend on a number of things. So a transaction, depends on some data on chain, which is to say that, you have to load some data from contract storage, let's say. So any sort of dependency of this transaction, anything any bit of the state that it touches, you have to actually post that state on chain and do these Merkle proofs showing that it's included in the kind of pre-state. So that's number one. Any contract that the transaction uses has to be deployed on the L1 in real time. And then, of course, you have to do the actual execution of the whole transaction. And then kind of in the post state, so any storage slots that get updated, you also do Merkle proofs of those against the post state. And then you sort of generate the post state root via all those updates. Okay. So the point is, there's all these stuff that has to happen. And all of that stuff, of course, is going to take gas. This is, I think, one of the questions that he sort of focused on, is if there's any cases where, like, a single round prod proof could end up taking a lot of gas. And yeah, I mean, you can imagine, right? I mean, it's we're talking about generalized Ethereum style computation. So if you think of, like, I don't know, some crazy flash loan style transaction, you're touching a bunch of contracts, you're updating a lot of state. You do have to sort of start thinking about this issue of, okay, what if we get to the point where the fraud proof is so expensive it can't fit in an L1 block, which would obviously be a serious problem. So to handle that, Optimism has this, they have this nice term, they call it, I think, nuisance gas, where basically within the L2, even in the optimistic case, they kind of have to keep track of how much a fraud proof would cost, just in case they have to do it, right? And again, keeping track of how much a fraud proof would cost is keeping track of all the stuff I just mentioned. It's not just a matter of execution, it's a matter of all of these Merkle proofs of all this state, it's deploying contracts, et cetera, et cetera. So that's another thing that kind of has to happen, just to make sure. There is this other way of doing it, and here's where, like, I don't want to, not sure exactly what they've committed to in terms of their approach. But in theory, you could also, if you want to avoid doing all this work in one transaction, you could split it up into multiple transactions, where essentially you have, like, you declare, Bob declares fraud, and then you post these bits of data sort of individually in separate transactions. But I mean, at the very least, if you do that, it's no longer really single round. And then I would just say that raises a number of other questions. But yeah, I don't know if Optimism is planning on doing things that way, but that is sort of another approach there.
Well, it's quite difficult because you have to have some way of sort of serializing or Merkelizing the full state of the machine between these transactions, right? Essentially, you have to save and restore your state, or you need to compute a hash of the full state of the system in the middle of executing a transaction, which is not easy.
Yeah, so there's the dimensional stuff.
You don't split the execution part into multiple parts. You have, like, a before you start execution where you, like, do a ton of transactions to supply all of the state. Like, you can't,
right?
You need to be able to execute, like, the actual execution in a single transaction for sure.
Right, the execution, right. The other parts of like posting all of these like, these data dependencies, you could maybe in theory split up.
There was, this is like way off topic. There was like an ETH research proposal that Daniel, you're probably aware of. I forget what it was called, where it was actually like doing like, so they were actually going to attempt to do like be able to prove a transaction over multiple rounds. Over multiple like L1 transactions. I don't know if that ever went anywhere.
Yeah, no, I do know what you're talking about.
That was some other optimistic rollup project.
Yeah. Right. Oh, I should know this.
It was one with like an anon founder, I think. Like
I'm blanking on the name now. Maybe Ben. I'm looking at Ben. Ben, your help.
Total digression.
But yeah, no, that's right. That was part of the approach. There was a whole post explaining that design architecture, which essentially a bit off topic, but long story short, has its own complexities. The other thing, of course, here is, so we haven't even talked about the execution itself, and maybe Harry, if you want to step in here, but basically there's this whole other component of actually handling sort of EVM execution that takes place on layer 2 and re-executing it on layer 1. That you have to sort of worry about if you're doing single round fraud proof stuff. You want to, essentially, long story short, here is there's this other component called a safety checker. I can maybe start it. Maybe Harry, you step in case I say something wrong. But essentially, what you basically have to do if you're like re-executing the EVM on executing something EVM like on L2 and then re-executing it on L1. Is any operation that's context dependent, you can't literally reuse the same EVM operation. So in other words, an operation that is not context dependent is like 1 + 1. It doesn't matter where you execute that, you're still getting the same result. If you're loading contract data from storage or, checking an account balance, doing that on L2 and then re-executing it on L1 obviously has to work differently because now you're in a different context. So in order to get this execution and have it be deterministic, there's this interception that optimism has to do, where they kind of intercept all of these operations and all of these particular context-dependent EVM operations and kind of replace them with their OVM equivalent. And this basically happens at compile time. When they compile contracts, they have their own fork of the Solidity compiler, which they did surgery on to sort of do what I just described. Does that seem like a fair summary, Perry?
Yeah. I mean, I think, just like zooming out slightly, like the reason why the thing about optimistic rollups is that you have to be able to so we're currently we're in the present and we're running a transaction and we're saying what the result of that is. And then when we prove it, we have to make sure that if it's valid now, then it'll be valid when we prove it. And if it's invalid now, it'll be invalid when we prove it. And maintaining that is really, really important, because otherwise you could have otherwise the whole protocol is broken, basically. And so how you kind of achieve that property of the proof kind of not being related to any external state is kind of, relatively straightforward for the kind of approach that we take, where kind of you're just emulating. Whereas for the approach of kind of containerizing, where you actually have to have untrusted user code running on Ethereum as part of the fraud proof process, while guaranteeing that code will run the same way at a later point as it does now, is kind of tricky, basically. And the only way to achieve that is by kind of severely constraining at the EVM level what sorts of code appears in it, and kind of being able to do that is kind of the tricky process, which involves kind of modifying the compiler in order to kind of output code of a very specific format that can be known to not cause trouble with proofs.
Yeah, and that, again, with them, that happens on the level of their fork of the compiler, which, I mean, we'll talk more about this later, but in our case, we can just sort of use the Solidity compiler as is, and then we compile EVM code. So it's sort of a post-compilation step. But yeah, we'll get more to that. But yeah, I mean, the sort of punchline with a lot of this stuff is all of those so like those particular complexities, those particular design complexities. One of the exciting things about, I think, the Arbitrum design is we just kind of avoid all of this. We don't really have to think about any of those things that I just mentioned. As Harry described, it's like this idea of worrying about, which operations are context specific and which aren't on Arbitrum is much more trivial, because ultimately all we're doing is execute a one-step proof. And if that requires a bit of context, we just give a bit of context. But we don't have to do any sort of like compiler surgery to get there. In terms of this notion of like, yeah.
I was just going to say, I think the biggest, and just, talking about it now, like the easiest way to, I think, describe like the huge difference here is basically in our, like a dispute in Arbitrum is resolved only running like smart contract code that like is kind of global over the chain. So like there's nothing kind of specific to what's being disputed in terms of like the contract code that's executed. Like there are, function calls, and like the input to those functions is obviously related to the thing being disputed. But like the actual code run is just like a single, or it's a couple contracts that like are audited and work, as opposed to basically having to have end user submitted code run as part of the fraud proof process, which is tricky to get right. Is very, very tricky to get right.
And it really expands the attack surface.
Yeah, because like, for anybody who's a Solidity developer, like, that like generally speaking, calling into untrusted code is really, really difficult to get right in the EVM, because the EVM is not particularly nice to use when it comes to these kind of trust issues. Like, your code, you write your contract internally, works fine. But the second your contract has to make a call to another contract, it gets kind of significantly more complicated.
Yeah. And in terms of like gas, as far as ensuring that we'll be able to actually execute this on L1, on Arbitrum, I mentioned it with Optimism, there's this complexity of this like nuisance gas tracking. On Arbitrum, it's just fairly trivial. It follows directly from the way the fraud proof process works, that each individual transaction that is required for an interactive fraud proof, has a clear upper bound, right? So there's basically these bisection steps, which all kind of look similar. We sort of know how much gas those will take. And then in terms of like the one-step proof at the end, some of those take, a different amount of gas, but we can just look at like the most expensive one, and it's still like well below the gas limit of a single block. So there's no additional calculation there to ensure that we'll be able to get this in on L1. So that's also nice. So we get all these nice, we sort of get to avoid these particular complexities in a very nice way. Okay, talk about downside. So downside to the multi-round approach, and I think like there's kind of just one in a way. Not that there's only one downside, but there's one that like sticks out, which is essentially
wait.
And this
I thought it was perfect. No, I'm just kidding.
It's near perfect, and even downside is hardly one. But so essentially, one of the this is a bit hard to. I'm trying to think of the clearest way to explain this, but basically, like the basic assumption that we have with Arbitrum is that if there is one honest validator, that honest party will be able to sort of gear things towards the truth. Yeah. And that's the same security assumption that something like Optimism makes, right? If there's one honest validator, they'll be able to issue fraud proof. For a given round of dispute, the sort of dispute process that Ed was describing, there is this possible case where both parties are being dishonest, right? So neither side is actually like bisecting, is sort of carrying out the protocol in an honest way. Maybe it's like the same person, just like wearing two different hats, trying to just confuse and screw up the whole thing. So what we need to allow for is the possibility, we need to allow for the possibility of this and say that, okay, after a given sort of, a bisection and one-step proof process happens, we need to sort of give the opportunity to challenge again, right? So essentially, this challenge process can be extended, and we have to allow for that, okay? And that, in and of itself is a downside. Now, with that said, it really isn't, for all sorts of reasons, it's not really the downside that it appears to be. So there's a few things to say here. I guess like number one is, so the idea here is if someone's going to do this, right, they're going to sort of slow things down and deliberately extend challenge. First of all, doing this is going to be very costly for them. So for every round that they lose, they're going to lose stake. And if you extend a given challenge multiple times, the amount of stake required increases. So with each round, you're going to lose more stake. So literally at a certain point, they're just going to run out of ether. Yeah, so that's just, and that is just sort of guaranteed by the protocol.
And just to amplify that, and it's not just that it costs them a amount that's linear in how long they delay. The cost of this sort of delay attack is exponential in the length of delay that someone is causing. Because they either have to come in with a lot of false stakes so that their people sort of pair up and challenge each other, or else if the system stalls, then the required stake goes up. And so either way, it's exponentially expensive to delay for some length of time.
Yeah. So that's the first thing. The other thing is like, okay, let's say you're doing this quote unquote delay. What are you actually delaying? And I think an important like aha moment with the Arbitrum protocol for me, when I was first learning about it, is even as a challenge is going on, in terms of what happens on L2, like L2 only interactions, let's say, the chain can just keep going, right? And this is essentially just like a direct consequence of the properties of rollups, where as a dispute is going on, any honest party can see, okay, you know, who's going to win the dispute? What is the valid assertion? What is the honest side? And they can just keep making assertions there. So this sort of the sort of state updates kind of splits into this tree. You have this invalid stuff going on. We say we don't care. We know that's going to get overturned. We'll just keep building on the valid side. And that's really cool because that means that, yeah, as far as like a user just using like, you know, an exchange or whatever on L2, they don't really have to be concerned with the fact that there's dispute going on, which is super cool. And I think that's kind of the most important thing to say here. But okay, like it does delay something, right? And basically the only thing that gets delayed are L2 to L1 messages, which is to say anything that's going on the Arbitrum chain that kind of in turn goes back and affects layer 1. And so if there's a dispute going on, right, layer 1, just by necessity, it's sort of the whole point of layer 2 is that layer 1 can't directly know what's going on layer 2. That's kind of where we get our scalability, which means that, okay, layer 1 has to just say, okay, we have to wait for this dispute to resolve before we make any updates that are sort of coming directly from Arbitrum. With that said, even with that caveat, okay, what's the most sort of important and useful and common L2 to L1 update? It's probably withdrawing ether or withdrawing some token. And if what you're withdrawing is a fungible asset, you know, we can use all of these sort of fast exit atomic swap techniques that, you know, we've included in our documentation, what we call like liquidity exits sometimes. So these are just like general techniques that are used, you know, other layer 2 protocols use these sorts of things where you don't have to directly wait for a dispute period. You can have a liquidity provider kind of help you out and swap your tokens out from layer 2 to layer 1. And the nice thing is, even in the middle of a dispute process, those still work, and those still work just the same way, and they work for the same reason, right? Because even while dispute is happening, any liquidity provider can sort of get this subjective perspective and say, okay, I can see which way this is going to resolve. I can see that this is a valid withdrawal. I'm willing to provide you liquidity now. And our general hope, and I would say actually our expectation, is that even in general, you know, regardless of a dispute happening or whatever, this will just be like the default way people withdraw from Arbitrum to Ethereum, is with these fast withdrawal techniques. In which case, so even in that case, even if there is some weird extended dispute going on, if you have these liquidity providers giving you liquidity, you don't even have to sort of wait. So yeah, what is, you know, a material difference and is something of a downside, I think practically is unlikely to really matter, which is nice. Cool. Okay. So what else? Moving on. Yeah. Oh, so the sort of last question that we got directly from Eric anyway, which I like this question a lot, is he asked, I'm just gonna read his question because I like the way he asked it. Putting the pure theoretics aside for a minute, have you noticed any perhaps counterintuitive or surprising second order effects with respect to tooling, UX quirks that differ greatly depending on subtle design differences between ORU design? The answer is yes. as far as counterintuitive or surprising, maybe more surprising to me than some of the other founders because I've been thinking about this stuff longer. But there are like interesting benefits to doing this this multi-round virtualization approach that have that show up. That certainly I didn't expect when I first learned protocol. Let's bring in Harry. I feel like I've been talking for a while, but do you want to?
Happy to.
Yeah, take it away. There's a number of things here, so whatever.
Well, yeah, but you said it was surprising benefits, so nothing.
Right.
Just
None of it surprised Harry, but things that may have surprised me.
You forgot to say boo if you wanted me to be surprised. Yeah. So I mean, it's an interesting question, and it's like it comes down to kind of like it loops back around to where we started, like the kind of the obvious benefit was the kind of not needing to do these intermediate state routes, and so having at this like base layer being more optimistic, and like in that kind of the optimistic case can be cheaper. But I think much more exciting is kind of like some of the compatibility benefits. And so kind of I think the one that like is kind of the thing that Arbitrum does very nicely is kind of make the user experience very similar to Ethereum, that have the kind of to have an absolutely totally minimized difference between kind of what it's like to develop an Arbitrum and to the degree of being able to take Ethereum code that worked on Ethereum and just port it and deploy it and have it work in kind of no time at all. The biggest thing there probably is native ETH support. Is that kind of on Arbitrum, ETH is the same ETH that's a native asset on Ethereum. Is ETH as a native asset on Arbitrum, and so kind of all of the code, all contract code that kind of support that uses like payable and receive and any of that stuff just works out of the box, which I think is pretty damn valuable in terms of kind of being able to provide kind of this quality, which is you can just deploy your contracts. Since there's obviously kind of a lot of like, because of the benefits that Ethereum gave to Ether on the base layer, it's kind of a very fun, it has a very fundamental role that just kind of doesn't, treating it as an ERC20 just kind of is doesn't give it kind of the same status as kind of people expect it to have and as it has on layer one. There's a whole different discussion about whether or not that was a good thing or not to kind of give Ether special status, but I mean, that's a very different conversation, since this is really more about kind of like compatibility as a benefit. The others, the fact that kind of the contract size limit, that Arbitrum, because basically we never need to, because basically if you deploy your contract on Arbitrum, the contract never needs to be executed on Ethereum. Ethereum's contract size limit doesn't affect us at all. That kind of there's no limitation from Ethereum on kind of how many bytes your contract can be, like there would be if you had to actually deploy and execute that contract on layer one, like in kind of Optimism's containerization approach. So that's definitely one.
Yeah, and in the containerization approach, you actually have a slightly smaller contract size limit, which I think is just because they have to run it through their custom compiler. The output the output EVM code is like slightly bigger. Yeah, so it's just kind of So, but in our case, we go that direction.
That's another case where kind of like I think there's a really nice advantage to like if it deploys on Ethereum, then it will deploy on Arbitrum. Because like I don't know about like anybody listening, but I'll say and just in the Arbitrum code base itself, even like there are a number of L1 contracts that are pretty damn near the size limit, and it'll like periodically go over, and then I'll do some refactoring in order to get it back under. And I think that's pretty common among Ethereum developers, just because the contract size limit isn't that high. So that's like a pretty significant class of contracts, basically, that like will just work out of the box on Arbitrum that would run into trouble. Kind of because of those limits on Optimism, because of the overhead, which is interesting.
Yeah. There was a question from, it's very confusing because several people have named themselves after me, but I know that
Daniel Goldman. Which Daniel Goldman?
from Daniel TechComs Goldman, which my understanding is Angela. Or no, wait, hold on. Daniel TechComs Goldman is, I'm so confused. The question I wanted to get at was the one for Angela, whatever she named herself at the time, which is like basically, you know, what's the connection between multi-round fraud proofs and like this ETH compatibility thing? And what I would say here is like, I mean, what we can say is that, you know, supporting ETH compatibility on Arbitrum was fairly trivial, right? We can just do it. I'm not exactly sure why this was harder on Optimism, but they currently don't support it, at least. So presumably there was some additional complication there. Yeah, I'd have to. I mean, it seems like, yeah, I don't know where exactly that complexity came in.
There's a really core trade-off here, which is like really interesting, and like a lot of things like skirt around it. A lot of like what they you know, when they talk about this, they skirt around it, we skirt around it, which is basically kind of like where you're maintaining compatibility. So like the Optimism team like is focused a lot on like minimizing the number of like software differences in the backend stack. So like, you know, I know that, you know, their kind of node is a modified version of Geth. At the cost of kind of decreasing their level of compatibility with kind of client-side tooling and with the EVM. Whereas we kind of make the opposite trade-off. Whereas kind of we have like a lot of custom software on the back end, but very, very aggressively maintain compatibility on the kind of user-facing side with Ethereum. And so the reason and all of that kind of goes deeply in line with kind of the same interactive like multi-round versus single round thing, because doing multi-round requires a lot more engineering, and it's taken some time to get there. We're there now, but it definitely took a lot of effort. Compared to kind of single round, all of the complexity, or almost all of the complexity, is like in the smart contract system that runs on Ethereum. And kind of all of the other parts are relatively simple, and that part's really complicated. But that part is exactly kind of what constrains what level of compatibility it's able to reach with Ethereum. Whereas Arbitrum doesn't really have any kind of noticeable constraints on kind of how compatible it can be or things that prevent that.
Yeah. So the bumper sticker version of this is basically our team deals with custom stuff, so you don't have to.
Yeah, I like that. We should make that bumper sticker.
And another good example of that is just the last thing I was going to say there, which is language compatibility. Because like Arbitrum doesn't have we don't need to have any sort of custom compiler. Actually, when you deploy your contract to Arbitrum, the L2 itself goes through a compilation phase. I'm not going to get into the details here of that, but like essentially the important thing is it's something you can totally ignore and don't need to think about at all. And so that means basically that any compiler that can compile for Ethereum, the output of that can also be deployed to Arbitrum. And so kind of we get the advantage basically of like the second a new Solidity version is released, you can immediately use it with Arbitrum, or you can use Viper or Yule Plus or
Yule Plus, whatever the thing Adler's working on. Yeah, even like if some new language emerges that doesn't even exist yet, if it compiles down to EVM code,
whatever one the EF is like sponsoring development now that's like forked from Viper or like Viper-like. I don't remember the name of that one, but yeah, whatever language.
Yeah, so that's neat. In terms of UX, that's obviously nice that we can support more languages.
Although I think personally, I'd say like the Solidity version one, it might even be the bigger deal. Like being able to use any version of the Solidity compiler.
Oh yeah. Yeah,
when a
for sure.
release comes out, you can immediately start using that with Arbitrum. There's no need to wait.
Yeah, and also it's just nice. This is less important, but in terms of tooling, it is just nice that like if you have whatever your contract deployment setup is, you can just point it to an Arbitrum node and it just works. You don't have to like intercept it first with some custom compiler thing, which is just cool. So you can just like use Truffle or Hardhat. So yeah, those are some of like nice UX gains that appeared.
But I think it's interesting. It really is surprising, like to get like that, like the degree to which like those benefits are like intertwined into the single round versus multi-round thing. Like there's a really like because, and it's really kind of nuts like how many far-reaching effects that has. The other thing to say is that like the point, this is like a little, kind of back to an earlier conversation, but like in terms of like single round versus multi-round and like virtualization versus containerization, you could do containerization with multi-round. You could do kind of like you could do that with multi-round, but you can't do virtualization with single round. You can only do virtualization with something which is like very, very, very EVM like, because it's way more expensive to actually run like you can't emulate a huge number of instructions. You can only emulate kind of a relatively limited number of instructions.
Right. You can only containerize something that's EVM like, right? Is that what you?
Yeah, exactly. And so kind of being like taking the containerization approach basically kind of like locks you in to being really, really, really EVM like.
Which again, like you said earlier, I think in terms of this idea of like where the complexity comes into the system, it's like, okay, we have this custom VM, so you have to like go through the work of creating that, and then once you sort of cross that bridge, so to speak, every like compatibility suddenly becomes a lot easier, which is it. And those are a number of examples that we hit on there. I want to just get at, there was another question. Okay, I think this was from Daniel TechComs Goldman, which is Ben. But asking basically, so to dispute you have to stake, and the answer there is yes.
No, that's angelfish.
You know what? Whatever. From Daniel Goldman, from one of my proxies, there was this. So the question that I see somewhere is, so to dispute you have to stake, and the answer there is yes. The sort of reason for that, I mean, in some respect, like you can imagine a version of the Arbitrum protocol that didn't require staking, where you could just like challenge, you could propose blocks and challenge without having to stake. It would like almost work in a way, like in the sense that the challenge protocol would still work. You would still enforce safety. The problem is now what's to prevent somebody from just griefing the network by doing a bunch of like BS challenges. And basically there is something preventing them, which is they're wasting fees. But we would rather have a stronger disincentive, which is once you lose, you get slashed. Also, because it's interactive, right? You're forcing someone else to step in and do their own transactions. We would like to reimburse. We would like to incentivize and reimburse that behavior. So we reimburse the gas cost and then some. We reward you for sort of winning a challenge. So this incentivizes challenges. So those are kind of the reasons that you need stake to participate. Although to be clear, it's not like you need to be. First of all, what you're staking is Ether, and it's not like you need to be pre-staked or something like that. You can just sort of sit there silently and have Ether ready in case you need to challenge. So it's not. There's no like proof of stake shenanigans going on here. Yes, good question, Daniel Goldman. Very smart person.
I think there are a couple more.
Let's see.
I mean, I think the important thing to recognize about the challenge mechanism is that it is very unlikely to. It's both incredibly critical for the security of the system and incredibly unlikely to ever occur, which is a weird combination. In that people need to be ready to use it, but it should not occur because basically there's next to no incentive to actually post something invalid, and B, if it does occur, the challenge period is a week. But it doesn't take anywhere near a week to actually resolve a challenge. Like in terms of, you don't need to use the full week. If you're operating efficiently and you're not being censored, you could do it. You could do your side much, much quicker. And so there's a fair amount of time to kind of coordinate around actually kind of, if this were to happen in the live chain, there'd be a pretty decent amount of time to kind of coordinate around kind of forming and participating in the challenge. It's not as though this has to happen kind of like live and dynamically super quickly. You could, you don't need to like sit around with like a full stake in hand, as long as you could, assemble a stake within, a day or two, you would still be totally fine. So I think that that kind of context on this is kind of valuable. That this is not like something that will be happening all the time, that you need to be ready to jump into at a minute's notice. This is something that kind of is a much rarer and can be, and potentially significantly kind of more high touch sort of occurrence. That the thing that you want to happen is you want to have people notice that something invalid has been posted, which is quite easy, and you want to relatively quickly respond, but it's certainly not as though there's kind of like a very short window and a massive rush to do so.
Yeah, there's a few related questions I want to get to. One from, I know it's Angela, so I'm calling you Angela. One from Angela about the basically whether this like interactive thing means that does this system is it part of the trade-off that the sort of challenger and the proposer have to stay live longer, right? And like does the interactive thing mean that we have to sort of keep stretching it out for each individual step? And an interesting bit of history here is, if you go back to sort of earlier versions of Arbitrum protocol, that kind of used to be the case, where basically each step in the challenge had a given amount of time, which meant that, the more steps that are involved, we can't quite predict how long it's going to take. But we since changed things. I think it may have been Stephen who had this insight. Maybe it was Ed. I don't know. Maybe just some combination of all of you. But basically now the answer is essentially no. The timing for sort of a given dispute, we do have this nice upper bound. And the easiest way to summarize it is it works the way chess clocks do. So each party has a total amount of time, and when it's their turn, their clock ticks. And if your clock runs out, you lose. So this way, in terms of time bounds, we can just basically essentially get like the same time bound guarantees as something like single round, which is very nice. Good question.
There is definitely kind of an assumption that like people who are running validators who are doing this will be running it on decent good machines with good internet connections. But like the nice thing about optimistic rollups is that you can assume that because basically you only need one valid node, because you only need one honest node, and so you don't need to kind of have anywhere near the degree Ethereum kind of you want to constrain very heavily. You want people to be able to run a node on a Raspberry Pi because kind of decentralization of the network is critical to its security, because it's kind of needs to have 51% honest nodes. Whereas kind of because Arbitrum because optimistic rollups in general don't have that sort of requirement, it means that you can compromise a bit more on kind of the hardware necessary to kind of efficiently run a validator without any sort of decrease in security, which is kind of very nice.
Another question I see, this one from David Haller, about essentially the fast asset liquidity providing method, this like liquidity exit thing, basically like where does this mechanism take place? And the answer to that is like this can be implemented just at the application level, and we already have a few applications that like we have a few applications on our testnet that are already doing that. So like we have support for Connects, there's the hop exchange protocol, but basically like all you need, the reason this can happen at the application level is like with something like Connects, you can just do this atomic swap where some party agrees like, hey, if you pay me on L2, I'll pay you on L1. You can just implement that at both ends. We also do have like a fast exit thing integrated directly like into our token bridge, where you sort of like track the withdrawals and then someone can like buy the withdrawal from you in flight. But yeah, there's all sorts of different ways of implementing this, and this doesn't have to be something like wired into the core protocol, which is kind of nice. In terms of the amount of time disputes take, I think like we're just like following the general. Oh, we lost Harry. Oh well. In terms of the amount of time dispute take, we're following just like the general community decision, which is probably arbitrary to be honest, but everyone's like going with a week, so we're going with that. And that's like the upper bound how long a dispute can take. So in other words, like
2 weeks.
I was going to say, it's really because there's two parties, the absolute upper bound. If you have two parties and they're both trying to delay the system, that dispute can take.
This is like, I can give like a quick summary of this because this is kind of interesting. Yeah, basically, like the reason why the dispute period and the optimistic rollup protocols are as long as they are is basically kind of this fear of like a long-term censorship attack against Ethereum. This kind of risk that like it's hard to really like analyze this risk. It's definitely kind of like, very much like an absolute worst case scenario, because if someone were to, for example, censor Ethereum transactions for a week, there's a lot of damage they could do to like, DeFi, like they could force liquidations, they could block Oracle updates, like there's all sorts of horrible stuff they could do already on Ethereum. And so that's kind of the kind of context for that. So basically the way that like the timing works for us, and the way to think about this is that like the thing that you want to make sure is that if a censorship attack occurs, there's time for it to be resolved using kind of, a hard fork in order to fix it. Or a soft fork, or, we don't need to get into the details, but essentially like, real human beings coming together, releasing a new software version that will resolve the issue, let's say. And that's kind of the reason why it's a week, is actually for that manual intervention process. So then the question is basically, how do you ensure that if there's a censorship attack, you'll have like that week window, you'll have that window of a week in order to kind of resolve it. And the way that we handle that is basically by kind of, I think the good analogy here is a chess clock. Each of the two people in the challenge have a week to do all of the rounds that they're going to do. So you have your week, and the other person has their week. In the happy case, kind of the parts of the challenge that you do, kind of in total will take minutes. There's kind of very little there's very little time that has to be spent like between seeing what the other person does and then being ready with your response. And so basically the only reason kind of the limit isn't like 20 minutes or a half hour is because of this sort of censorship thing. And so basically kind of what we do there is we say, well, let's say you start being censored, and Ethereum, and kind of so there's some attack on Ethereum, there's like a 51% attack or something, and you're being censored. And this is going on. And then basically the attack is broken somehow, but it's broken in a way that now you're no longer going to be censored. So then you should be able to finish up the rest of the operations that you have to do in the challenge relatively quickly. Because if there's a serious censorship attack and it's solved, there's not going to be a new one immediately thereafter. If we solve the censorship attack, we're going to solve it for the entire challenge. And so that's kind of where basically this chess clock idea comes in, is that we're factoring in like at some point in the challenge, there could be kind of a censorship attack causing a really long delay. But it's not going to happen multiple times. And so that's kind of like why basically the entire challenge has 2 weeks, because each party has their week. And one kind of interesting thing there is that it's not even a week from when it's not even 2 weeks from when the challenge starts. It's 2 weeks from when the kind of original node that's being challenged was created. Because basically the reason for that is that if an invalid node is posted, any other validator on the network or who's running an Arbitrum node will see that was invalid. And that somebody should at that point post a valid node. And so essentially kind of the week is basically, that's essentially a roll-up block. That's essentially the first move in the challenge is basically kind of posting that contradictory claim. And so if you take a long time to do that, you're essentially kind of you're delaying getting into the challenge. And so that's kind of already eating away basically at your week of time. Now a week is a long time. So it's not as though there's like a huge rush here, but it is kind of when the clock starts counting.
Mm-hmm. Yeah, and then in the sort of happy case, when there's no challenge, it just takes a week for a transaction to finalize, which importantly means like for a withdrawal, that's when you've executed. Which hopefully that answers your question. 1 week,
so it's like 1 week for the asserter and 1 week for the challenger. So kind of in basically the worst case there is if the challenger, if someone is malicious and kind of manages to challenge themselves. Then that's kind of where you get to like the 2 weeks worst case. If kind of one of them is, if kind of there is a dishonest assertion and an honest challenger, then the worst case will be slightly more than 1 week.
Mm-hmm. Yeah. Which again, and yet again, if you're doing that, you're essentially just burning your own money. So, but yeah, no, as far as like this week-long parameter, when I say it's arbitrary, I mean, it's, it's just sort of something the community has kind of converged on as, again, like, if there were this L1 censorship attack, which of course would just be very bad generally, vaguely speaking, what is the time it takes for like some sort of social consensus to emerge, and to do something about that? So yeah, we're just sort of like piggybacking off of that and, veering on the conservative side there.
Yeah, and just the one more question came in, which is, if it was, two honest parties that were somehow engaged in a dispute, yeah, they could finish it super quickly. I don't know if I mean, it'll be 5 or 6 transactions total, so it's basically kind of however, maybe 10 minutes, but there's no sort of.
Exactly. There's no reason not to just like do your side of the interaction right away. So then,
after the challenge is over, you can't confirm the underlying node. The other thing here is that there is also kind of no node will be confirmed in less time than a week. Since if there's a challenge that's resolved quickly, if that you still need to kind of allow time for other challenges to come in. And so sort of there's a kind of a week, the week period, which is kind of the time that the node could be challenged, is kind of set in stone there, regardless of kind of whether or not a challenge has kind of started and finished before that week is up.
Yeah. Next time maybe we'll just get you on stage, Angela. We have a lot of specific questions, but yeah, hopefully that kind of clears it up. In terms of the timing and with this multi-round process. I see we're at an hour.
It's really subtle, and like we didn't realize that we could do this for a long time. And when we figured out that it was possible, because like for a while we had kind of thought basically that you had to provide a separate time period for kind of each round of the challenge. And it was really kind of like digging into the details of basically like why you have to assume kind of a potentially long censorship time and how resolution of that would look like. That we kind of came to this design where you can actually have sort of a week between all of the moves.
Yeah, essentially like what is the actual risk you're mitigating? And as you said earlier, once you realize it's this like extended censorship risk, just giving this extended time for a transaction is effectively the same security assumption as So like a censorship attack would be very bad for L1 and for L2 regardless, and like this doesn't actually change that or make that any worse. So it's a very nice improvement we made. And again, when I say we, it was not my idea.
But essentially, like the challenges will only these essentially kind of only happen in the malicious case. And so like I think and I mentioned this periodically, but the important thing to highlight here is that like this is something weird and malicious is happening if you get into this situation at all, which the protocol needs to be able to nicely handle and does, but it's not the sort of thing that will kind of happen in kind of regular functionality. Because basically, if it's happening, somebody's committed to losing a large amount of money, which is not something that somebody will likely do freely. And losing a large amount of money for kind of the only upside to them being they've managed to delay withdrawals for some amount of time. And so kind of the upside to them is quite low, and the downside is losing their stake.
There you go. So it's very important code that should rarely, if ever, have to run.
Yes.
Yeah. Okay. There's more questions. We can keep answering those in general. But I think it's probably about time to wrap. Thank you for all the good questions. Appreciate that. Good protocol related questions is fun. And we'll post this recording first of all. Hopefully this was helpful and interesting. Obligatory reminder that we are hiring. And there's all sorts of positions open, so you can reach out to us various ways. Dan Berg there in the audience is probably the first person you'll be speaking to. And thanks for joining. This was fun.
Yeah. These are awesome.
Yeah. Anything else?
Thanks for organizing and cloning yourself.
Yeah. No, I asked a lot of great questions. Yeah. I'm really proud of myself.
I think you might need to like do some like return, like fire back some like change your Twitter name.
Yeah, I'll change my Twitter name or Discord name to some combination of like Angela or Ben. Yeah, that'll be my next step. All right, cool. Yeah, and we'll be doing more of these. I don't think we have a next one scheduled yet, but just keep an eye out on Twitter and so on. And probably the next one will be something more open-ended Q&A style. Cool. Alrighty. Signing off. Thanks, Liz.
Thanks for joining.